During this talk, we will go through 4 key areas within this paper, namely the problem statement and the related work, the contributions that this paper made, and then finally the experiments and a quick wrap-up of the results. Our problem statement was, going into this, how sensitive are behavioral analysis tools to adversarial perturbations? Throughout this project, we employed the Stratosphere Linux IPS software created by the Stratosphere project by a research team in the Czech Republic. This software is able to model characterizations of network flows as Markov chains. It takes as input network flow size, duration, and periodicity in order to form a chain of states which can then be used to characterize the behavior of network traffic. As you can see in the table below, it can describe parameters such as network flow size, duration, and the periodicity. By combining a sequence of the below parameters, Stratosphere can characterize the behavior and long-term behavior of network traffic. Stratosphere also has a way to define time between network flows, which heavily affects the periodicity of network flows. It has been defined as symbols, which in this case can be seen as a dot, comma, plus, star, or a 0, representing the lengths of time between network flows between each flow, as seen in the table below. The characterization of a network flow can then be generated by the combination of these characters. For instance, as seen in the below pattern, the Cridex Trojan can be formulated through a Markov chain of the below parameters. Now we will go into the contributions that this article has made to the research community. 4 main contributions were made to this project. First off, we implemented a packet capture parsing module which would consume the malicious packet capture files, which we would later manipulate. Then we created a network flow timestamp manipulating software in order to provide support for perturbing parameters on the network flows. Third, we created a set of stochastic search algorithms for actually providing the perturbation to the parameters. And then we also created an automated gray box testing scheme of the Linux Stratosphere intrusion detection software. Here is a high-level overview of our implementation. By taking a packet capture file containing malicious network traffic, we can feed it into our parameter perturbation engine and tune the characteristics of malicious network flows to create a manipulated packet capture file. We can then feed this into the Stratosphere Linux IPS system in order to hopefully achieve mischaracterization. We would like to investigate how much perturbation we would need to provide to each parameter in order to achieve this mischaracterization. Because we could not arbitrarily change the size or content of a network packet without destroying its malicious properties, we decided to omit the size parameter for each packet network flow. We were then left with the parameters duration and time between network flows to operate on. We use Argus's definition of a bidirectional network flow as a baseline definition. We only investigated IPv4 traffic, and we used network flow captures from the Cridex Trojan and from ZBot malware in order to manipulate those. In order to create a packet capture parsing module, we had to create software that was able to consume a PCAP file, a packet capture file. We did that by implementing classes for packet and flow, and we parsed these using the Python package called Scapy. We would then have access to all the contents of a packet capture file in Python directly. We then proceeded to implement software for manipulating the actual timestamps of network flows. This function took as input a packet capture file and a set of perturbation parameters. It would have to identify the relevant network flows and their behavioral attributes, such as duration, size, and time between current flow and next flow. The perturbation parameters would then be applied to those relevant network flows that were identified. The program would then return a new packet capture file with the same connections in the same order, but with timestamps modified according to the parameters. The below figure describes how network flows timestamps could be manipulated. So, after identifying the time between flows, and the time between the previous flow and the current flow, and having access to the perturbation parameter for which the flow should be altered, we could then decrease the start time for a flow and accordingly decrease the end time for a network flow. Of course, by manipulating the timestamps of one flow, this may affect the timestamps of all the packets within that network flow. Since a network flow may contain an arbitrary amount of network packets, we would have to manipulate the timestamps for every single packet within that network flow. The manipulation scheme for each packet could be seen in the figure in front of you, where you would need to have a new end timestamp for the entire network flow, and then decrease or increase the timestamps for each packet accordingly. After this process has been completed, a malicious packet capture file can then be sent into Stratosphere Linux IPS as seen in the image in front of you. However, we would still need to provide actual parameters for the perturbation engine. These parameters would determine to which degree the network flows will have to change after being manipulated. We want to change them for a reason, and for that, in that regard, we select a set of objectives. We can represent these objectives as functions in our stochastic search algorithms. For instance, we may maximize throughput for the connection by decreasing the duration of network flows. An attacker may want to maximize throughput in situations where exfiltration of data, for instance, is necessary. We also wanted to investigate what is the minimal change that we can do to original network traffic while it still remains undetected. So we could do this by measuring the magnitude of perturbation and minimizing the Euclidean distance between the manipulated packet capture and the original packet capture. We selected two primary ways of searching for new parameters. One, the random search and adaptive step size random search algorithms. And secondly, the simultaneous perturbation stochastic approximation algorithm, which is useful for noisy measurements, and network flows could be seen as a noisy data. Going into the most interesting algorithms of these, the simultaneous perturbation stochastic approximation algorithm. This is a procedure where you can find roots of equations when there are noisy measurements. As network traffic may be subject to unforeseen and spontaneous altercation, network traffic could be seen as noisy. Measurements, however, of the objective function must then be approximated, since we cannot rely 100% on noisy data. The SPSA algorithm requires a set of arguments, as seen on the page in front of you. It requires an objective function with added noise, a gain sequence A, another gain sequence C, and a Bernoulli value for each parameter. For each iteration of SPSA, we computed two noisy measurements of the approximated objective function. We then computed the approximation of the unknown gradients. We then did an update of the estimate for the SPSA function. The SPSA algorithm terminates if little change is observed over several successive iterations, or if it's not, then k is incremented and a new iteration on SPSA is initiated. Each iteration over SPSA will provide a new set of parameters based on the gain sequences, the noisy objective function, and the measurements acquired by these. However, as SPSA relies heavily on deciding on the correct gain sequences, and since this is not a trivial task, we thought it would be interesting to dynamically modify these using a machine learning approach. So we implemented a learning automaton for optimizing gain sequences. The learning automaton would provide the SPSA algorithms with new parameters for gain sequences for each iteration. It would investigate whether the end result was that the network traffic file was detected or whether it was not detected. Good solutions were rewarded by increasing the probability that they were selected the next time, and bad solutions were penalized accordingly. We will now take a brief look at the experiments that were conducted by using the before mentioned techniques. Okay, so quickly to reiterate, we would like to investigate how much perturbation is needed to achieve mischaracterization. Also, we would like to adhere to the underlying objective function, which could be to decrease the difference between the new manipulated network flows and the original network flows, or it could be to maximize the throughput by decreasing the duration of network flows. The experiments were conducted through the use of several containerized applications. We deployed one container for each experiment. One container contained the adaptive random search, one contained the adaptive step size random search, one container performed the simultaneous perturbation, and we had another container doing the full-on experiments using the learning automata. For each of the applications, we experimented with the two different objective functions. We will now take a brief look at the results that were gathered as part of these experiments. First off, how well did the random search and adaptive step size random search perform? We provided some initial thresholds for these search functions. Since they require thresholds to operate, we had to provide them manually, and we did so for each iteration. Note that this overview does not include any optimization on the learning automata. Note that this experiment was not seen as a means of providing intelligent perturbation parameters, but rather as a means of identifying to which degree the network behavioral analysis tool was sensitive to perturbations. So we provided initial manual thresholds, and by decreasing them significantly for each iteration, you can also see that the magnitude of perturbation decreases accordingly, from a top of 150 in the first iteration to a top of 1.5 or a bit more on the second and the third iteration. As you can see in the results table in front of you, by the third iteration, the change to the network traffic was so small that it actually was detected. However, by increasing the mean magnitude of the perturbations slightly, it can be not detected by the intrusion detection system. We then proceeded to attempt to make or generate parameters more intelligently using the simultaneous perturbation stochastic approximation algorithm. On the CTU-108 NXS, the CRIDEX dataset, we ran 4 experiments with 50 SPSA iterations for each experiment, using the 0.1 and 0.9 matrix as initial gain sequence values. The mean magnitude across all experiments resulted in 4.18, which is quite significant and means that a pretty large degree of change was required for it to evade detection. However, as the variance between the experiment was 2.18 on the same scale, this could imply that gain sequence parameters were not sufficiently tuned. As a result, we wanted to make more intelligent decisions when it came to gain sequence parameters. So we deployed our learning automaton in an attempt to generate better gain sequences. This approach would try a set of gain sequences and then see the results based on whether the final packet capture file was detected or not. It will also take into consideration the magnitude of the perturbation and in an attempt to lower this. Using this technique, we were able to reach a lower magnitude of 0.9. However, the learning automaton only ran for 15 iterations, and this is absolutely not enough. More iterations are needed to conduct a proper experiment for this. With an overall objective of reducing the magnitude and the Euclidean distance between the original network traffic, we again deployed the learning automaton for 25 iterations to tune gain sequences. Using this technique, we were able to reach a lower magnitude of 1.4. Again, far more iterations were needed to perform a proper experiment on this using this methodology. Through this work, we uncovered that by adding small perturbations to network flow parameters, it may be possible to evade behavioral analysis intrusion detection systems. Small adjustments to certain behavioral patterns could then increase the risk of malicious network behavior not being detected by a behavioral analysis system. As future work, we would like to implement support for larger packet captures by improving the parser using B trees as a data structure. We would also have to perform a configuration review of the algorithms themselves and then run vastly more iterations on the learning automaton and SPSA algorithms. Thank you so much to Professor Anis Yazidi and Horik Haugerud from the Oslo Metropolitan University. Also, a great thanks to the Stratosphere Linux IPS team who has created great software for use in the open source community.